Should I start?
I was going to announce you. So thanks everyone for coming to the third day of this workshop on model theory and combinatorics. This morning we have Abdul Basit, and he'll be speaking about point box incidences and logarithmic density of semilinear graphs. Thank you.
Hi. Yeah, thank you for inviting me. And yeah, like I said, so I'll be talking about point box incidences and semilinear graphs. So I'll start off with a very simple sounding problem. So if you get bored at any point in the talk, you can just start thinking about this. We managed to give some bounds for it, but we're still a couple of logarithmic factors off. So, but yeah, here's the problem. I'm given n1 points and n2 rectangles with axis parallel sides in the plane R2. And I have the condition that no k rectangles have k points in common. And the question I want to ask is, well, what is the maximum number of incidences that we can have? So if you're not familiar, an incidence is a point rectangle pair where the point lies in the rectangle. So maybe we can do a nice example. So yes, here's a configuration where no two rectangles have any 2 points in common. And I think I get 9 incidences. So I wrote something at some point. Yeah, here we go. I think my point. Okay, yeah. So this point is in one rectangle, that one's in 3, and you can count. And in total, I think we get 9. And well, this condition isn't too hard to check, but you can trust me on it. Okay, so we want to try to count the number of incidences, and I guess the question is, well, why should there even be a non-trivial bound? So, and we'll see why. We do need a condition like this. So no k rectangles have any k points in common, because if you don't, then what I could do is just do a trivial, take a bunch of nested rectangles, put on my points in the innermost one, and then I have the maximum possible number of incidences. Okay, so that's the big or general question that you should have in the back of your mind. And I'll try to give some bounds for it and build up some theory as we go along. Also, if there's any questions, you can just stop in the middle. Okay, so the more general context is this thing called Zarankiewicz problem, which is a question in extremal graph theory. So the setting is this: I'm given two numbers, s and t, natural numbers, and I want to look at the complete bipartite graph KST, which has s vertices in one block and t vertices in the other. So I get a bipartite graph. I have s vertices here, t here, and everything is connected to everything else. So given some s and t, and I say, okay, if I take another graph that doesn't contain a copy of this thing inside, what's the maximum number of edges that I can have? So this is a very old problem in extremal graph theory, and we have some bounds for it. So we'll see what. Okay, so here's a theorem of Combinatorics, Shorsh, and Theorem from 1954, which says, well, okay, assuming that s is less than t, the number of edges is at most n to the 2 minus 1 over s, and then there's some constant that depends on s and t, but we won't worry too much about constants for this talk. Okay, so the main thing you have to look at is the exponent, so which is 2 minus 1 over s. Okay. So that's a theorem from 54, and it's quite simple. So I think I'll maybe talk a little bit about the proof. So here's the proof when s and t are both 2. What we're going to do is, so it's a very standard proof in combinatorics, quite nice. What we're going to do is we're going to count the number of stars. So I count the number of structures that look like this. So U is on the left side and V and W are on the right side. So count the number of stars, and we can try to count this in 2 different ways. So, okay, what can we say? Well, the first thing we can say is if I pick a vertex on the left side and the degree is U, so D of U is the degree of my vertex, then there's D of U choose 2 ways that I can get a star that's centered at U. So that's one of the ways we count it. And the other way we count it is look at the right side. Well, an obvious upper bound is just the number of vertices on the right, choose 2. And that's basically the proof. So we say, well, this sum is at most we choose 2, size of V2 choose 2. And then using Cauchy-Schwarz, you can get the bound. Well, what's the bound in the 2 case? I get ordered n to the 3 over 2. So that's basically the proof of Combinatorics Theorem. The general proof is also the same. what you do instead of counting this kind of star is now you can count that kind of star, and that's how the proof for the general case goes. The argument is essentially the same. You use Holder's inequality instead of Cauchy-Schwarz. Okay. Are there any questions?
Wait, I missed why you used the fact that it was KST3. Sorry.
Yes, it's being used here. So, for example, if I pick two vertices, there's at most one vertex U that I can pick, which is saying Q is at most V choose to. V2 size of V2 choose to.
Okay, yeah, thank you. Yes.
Right. Any other questions? Okay, so yeah, this is essentially the best upper bound we have, and it is actually conjectured that this is the best possible bound. And that's probably one of the more central questions in extremal combinatorics is, can we show that this bound is tight? And we know very little about this problem, unfortunately. So here is what we do know. Okay, so there's matching lower bounds for S and T equals to 2. And you can get this by looking at the incidence graph of points and lines in the finite projective plane. This is an old result from, like, it's a folklore kind of thing, but I think probably it goes back to Klein from 1938. For S and T equals to 3, you can take a point sphere incidence graph and then again argue it doesn't have a K33 and the number of edges is the right one. And then there's algebraic constructions over other finite fields. This is a result by Alon, Ronya, and Szabo from 99. And that only works when T is much, much larger than S. So T is bigger than S minus 1 factorial. And yeah, so that's essentially all we know. I think we also know, so when S is 2 and T can be anything, and S is 3, then we have more constructions that show tightness. But other than that, not too much. So these are all algebraic constructions over finite fields. And then recently, this was a result of Book. And what he managed to show is, well, something in the same way. But again, T needs to be pretty large. It needs to be exponential in S now. So roughly 9 to the S. And there's this idea that, so all of these were deterministic algebraic constructions. This last one takes a random construction, so it mixes algebra and randomness, and you can get a little bit better. No, so this is a recent result of Book. Right. And that's basically all we know about the lower bounds. There's been some work on the constants, but like I said, I'm not worrying too much about the constants for this talk. So that's essentially the state of the problem. Okay, so why is this important? Because this gives us a bound on my question. So if let's go back to the axis for rectangles and points. So I have n1 points and 2 axis parallel rectangles. And I look at the incidence graph. So the incidence graph is my left-hand side, V1 corresponds to points, V2, the right-hand side corresponds to rectangles, and I put down an edge if a point is in the rectangle. And by my condition, so for example, for this configuration, there's no two rectangles have 2 points in common, which means my graph doesn't have a K22. So there's a direct translation. So automatically, I get by the Kobayashi-Shorter theorem that the number of incidences looks like n to the 2 minus 1 over k. Yeah. So we can get some bound. The question, well, we'll see how to improve this bound in a bunch of different ways. Okay. So like I said, the Kobayashi-Shorter theorem, it's conjectured to be tight, but then there's a bunch of results that say, okay, what if you look at graphs that are simpler in some sense? So one of the basic questions you can ask is, well, what about graphs with bounded VC dimension? So what do I mean by the VC dimension of a graph? Well, I take a bipartite graph and I look at the neighborhood of a vertex V on the right side. So I have V1 and V2. I pick a point here and look at all the vertices that it's connected to. So that's the neighborhood of this vertex V. And I look at the set system, which is the set of neighborhoods of everything on the right. Okay. So this gives me a set system, and the VC density or the VC dimension of the graph is the same thing, is defined to be the VC density or the VC dimension of this set system. So that's at least in combinatorics how we define the dimension of graphs. So here's a theorem of Fox, Bach, Scheffer, Fuchs, and Zal from 2012, which says, well, if I have such a graph and I look at the set system, if the shadow function is bounded by z to the d for all z, so that's saying the VC density is at most d, then and g is kk, it's kkk free, then the number of edges looks like 2 minus 1 over d. So it's quite a bit better, right? Because recall that the Kováry-Schaaf theorem, the bound that gave me was n to the 2 minus 1 over k, right? And this constant also depended on k. So I have some constant that depends on k. But now the constant is depending on k, but the bound is actually just depending on the density, the exponent. So it's quite a bit better. And the proof is very combinatorial. I won't say much about it, but aside from the fact that it uses this packing lemma of Hausdorff, if you know what that is, that's what the proof relies on. And more recently, there was a slight improvement. What's the slight improvement? That's by Janzer and Pohota from last year. And what they show is if we have k and d both being bigger than 3, then you can do a little bit better. Well, and they don't really quantify how much, but it should be little o, so strictly smaller than 2 to 1, 2 minus 1 over d. Yeah, so I guess an open question here is, well, what should this be exactly? What should the exponent be here? So for example, to prove this bound, what they end up doing is they have a very different technique and they use this hypergraph remover lemma. And then potentially if you have a better hypergraph remover, so this hypergraph remover lemma works for all hypergraphs. If you have a hypergraph remover lemma or regality lemma that does a little bit better, then potentially for bounded VC dimension graphs, then potentially you could quantify what this exponent should be. So yeah, that's an interesting question. I think it's interesting. Okay, so yeah, that's for bounded VC dimension graph. And again, the VC dimension of rectangles is 3. So this automatically gives us a much, much better bound. It gives us n to the 5 over 3. So now the exponent does not depend on k, and we have a much more concrete bound. For every k, I know that the number of edges is at most n to the 5 over 3. Okay, so I seem to be going pretty slow, but it's fine. Okay, so the next step forward is semialgebraic graphs, which are a little bit more restricted in VC dimension. And for this case, we can say we have this theorem for, again, Fox, Scheffer, Fuchs, and Zal, which they say, well, if you have a semialgebraic graph in RD1 times D2, then the exponent, well, it's still independent of k, and g is kk free. It's still independent of k, and now you can do a little bit better than what you had before. So this c doesn't really depend on the VC density anymore. It depends on just the dimension of your defining variables. Oh, yeah. Oh, your parameter space. Okay. And for this, they use, so I think this is a very nice thing. So I'm quickly going to mention. So how do you get a bound like that? They use this thing called the polynomial partitioning theorem. So this very strongly uses the topology of the reals. What does the polynomial partitioning theorem say? Well, very informally, if you're given a set of points, so here's a bunch of points, I can find a polynomial of small degree. So I want to partition my point set into r equal parts, at roughly equal parts. So that's my parameter r. And it says, well, there's a polynomial of degree at most r to the 1 over d that basically does this, or that does what you want it to do. It partitions your point set into the r parts, or equal parts. So what they end up doing is they use this theorem, the polynomial partitioning theorem, combined with the bound from the previous slide. So theorem, which was it? Yeah, the VC dimension theorem. So so how does it work? You partition your point set into some number of parts. Inside each connected component has at most n over r point. So you end up using the VC the VC density bound inside each cell, and that ends up giving you an improvement. So that's roughly how you get better bounds for semi-algebraic graphs. Right, and then we know that the point rectangle incidence graph is semi-algebraic. You can parameterize rectangles by R4. And then this theorem that we have, it implies a little bit better. It implies n to the 10/7 instead of 5/6. So, okay. So a little bit better bound. Wait, 5/3, that should be 5/3, I apologize. Okay, and yeah, maybe I should mention this thing as well. Oh, yeah, just one thing. We should expect better bounds because for semi-algebraic, so I think we've seen this kind of phenomenon before as well, where I have something that's being defined using product and multiplication and addition. But if you look at the incidence graph of points and rectangles, it's really simple. It's only defined using ordering. So we should expect significantly better bounds in this setting. So that's what we'll see next. So I'll mention our main theorem soon. But even before that, I think I will probably want to say this semi-algebraic graph result, it was put in a more general context where Artem, David Galvin, and Sergey, they showed that for Disto formulas, you can get a bound that looks similar. They don't exactly quantify what C should be, but it depends on the complexity of your cuttings. So they end up using cuttings in solid decomposition. So C depends on the complexity. So yeah, it's a generalization of this guy. Any questions so far? Okay, so yeah, this is our background so far. So what can we show as a result, our result, like with me, along with Artem, Sergey, Tao, and Min. So we show that if you have n1 points and two rectangles, again in R2, and there's no KK in the incidence graph, then you can basically get almost a linear bound. So n log to the 4n. So significantly better, right? I mean, now we're basically down to essentially the best possible thing you can say, aside from the log factors. Okay, and then what else? So yeah, this is the first point is a consequence of a much more general theorem. So I'll try to talk a little bit about that one. But we also have, so this uses ideas for model theory. The next part, these guys use only combinatorial ideas. If you have what we call dyadic rectangles, so the rectangles are products of intervals that are dyadic, then we can get a much better bound. So we get a logarithm out n log n divided by log n. And we can also show that this is basically tight. Well, it is tight aside from the constant. So there's a lower bound that for every n, we can find a set of n points in rectangles, which gives us the same number of incidences. And it's K2 free. So it's basically best possible. So what we do not know, for example, is, so I guess there's an open question is improve the log, the exponent for the log. So if you've been thinking about this and you figured it out, you could let me know. Okay, so that's what we have. I think if I were to conjecture something, I'd say it's probably log n, but I'm not sure. But we do know something a little bit better. Yeah, so that's the question that I just mentioned. We do know something, and this was a result by Timon and Zakharov also last year, and they showed when k is 2, then you can improve this bound to n log n. And then they use the very combinatorial ideas. So this notion of separation dimension, buffer dimension, and they also end up using our construction in some way. Yeah, so for k equals to 2, we know what the right bound should be, but not for larger k. Okay, right. So I said I'd talk a little bit about how we get this theorem. So this is a consequence of a much more general theorem. What does the more general theorem say? We look at these things called semilinear graphs. So now you have a semi-algebraic graph, at least. And now I restrict my inequalities to be linear. So again, I have my vertices are points in RD1 and RD2, and I have a system of linear inequalities, and my relation is given by this system of linear inequalities. And then what we end up showing is essentially the corresponding thing, is that if you have such a graph, then the number of edges is bounded above by n, some power of log to the n. And this power of log is precisely the number of inequalities that you need to define the system, which is how we got the 4 in your in the rectangles from. So if you have boxes in 3 dimensions, you can get a bound that looks like n to the 6. Yeah. And then the theorem is actually more general. We can replace any order division ring, and we define these things called coordinate-wise monotone functions. Maybe I won't talk about what these are, but yeah, it's a little bit more general than what I've stated here. But the open questions, there's a couple of open questions. Well, does this power of log actually need to be there? I think we know it does, but does it need to grow with the number of linear inequalities? So if you add more linear inequalities, do we need to have more logarithms to cater for that or not? We don't have an answer for that. Okay. Yeah, so maybe I'll quickly talk about the proof idea, I guess. Okay. So we're going to do induction on the number of linear equations. So again, if you stick to the reals, then things are quite a bit simpler. So that's what I'm going to do. And let Fsn be the maximum number of edges in a KKK free graph that has n vertices and is defined by S linear equations. Okay, and then for the base case, well, if you have if f is 0, then it's easy to see you have a bound of at most k times n. So that's our base case. In the other case, like I said, we do an induction. So what we end up showing is an inequality of this form. So basically, we're going to do a divide and conquer approach and get this inequality. I'll say how, but well, we go down in the number of equations, or we go down in the number of variables. Yeah, either way, we gain a little bit. So how do we do the induction? We look at one of the defining inequalities and separate it up by the variable. So let's say my defining inequality looks like L1x is less than L2y. I'm going to map everything to the reals. So this is what I should get. So, okay, I have V1 that gets mapped to the reals and V2 that gets mapped to the reals. And I find a point that bisects everything. So this is precisely half my vertices. That's precisely half my vertices. And now it's kind of, because my inequality looks like this, it's kind of easy to see what should be happening. If I look at things that go across, so V1 plus and V2 minus, then I should have no edges in this case, right? Because they basically don't satisfy my inequality. If I have things that go here, then I should get the complete graph. Well, I should get, everything should depend on the remaining inequalities. So I go down in the number of inequalities. And if I just restrict myself to these guys, then I've decreased the number of vertices. So that's where I get the remaining 2 from. Yeah, so hopefully that gives a very rough idea of what the proof kind of looks like. And then that gives us the thing we want, and that's almost the proof. Okay, yeah, before I move on, does that, any questions about this? I think I should also be winding up soon. So, right, how much more time do I have?
You have 5 more minutes.
Oh, okay. Okay, so yeah, so that was about graphs. There are extensions to hypergraphs. So like R-partite, R-uniform hypergraphs for order relations. So here's a theorem of Erdős, which says, well, if you have an R-partite, R-uniform hypergraph, again, total number of vertices is n, and it's k free, so the corresponding thing, the complete hypergraph. Then the number of edges is bounded above by some polynomial in n that depends on k and r. Okay, so basically what you think the extension should be. And there are lower bounds that say essentially that this is as good as it could be. Aside from some constants, you can't really do too much. And so you can substantially improve this bound. But again, if you go to semialgebraic and things like that, then potentially this could be improved. And this was shown to be the case by Tao Do. She said, again, if you have a semi-algebraic hypergraph, then your thing should depend only on the dimension of the parameter space. So the dimension of your objects. Okay, so that's for semi-algebraic. And what we end up doing for semi-linear hypergraphs is basically the best, again, that you should expect to say. We just say, well, the number of inequalities is at most, the number of edges is at most n to the r minus 1. Again, times some logarithm where the power of the log depends on, now it depends on r and the number of defining inequalities. Okay, the proof is essentially similar. You do a double induction. Now we have to do an induction on the uniformity as well as the number of inequalities. So that raises some, it makes things a little bit trickier, but not too much. So yeah, maybe I'll skip the rest of this. Okay, so yeah, maybe we can talk about some consequences of what else can we do. So for example, if I have so far I've been saying, well, you look at the hypergraph and it's KKK free. But if we say that the defining relation is itself KKK free to start off with, and then any hypergraph must be KK free, then we can get a much stronger bound. So well, we can get rid of the power of the log. So right, yeah, so sorry, what do we say? If the defining relation is KKK free, then the number of edges is just n to the r minus 1, and we get rid of the power of the log. And as a consequence, it gives us some way to combinatorially characterize modular structures, modular or minimum structures. So yes, here's a fact from 98 where O minimal saturated structure, well, it has to define a field if it's not locally modular. So what we can say is, well, any O minimal structure, if it's weakly modular, then every definable relation, you satisfy this kind of property where the number of edges is bounded above by n to the r minus 1. So that's one thing, and I guess this is more ongoing work with Min that I'll quickly talk about. So if we look at the relation R, and I can define the upper density of this relation to be basically the maximum exponent that I can use to bound the number of edges. And then we can ask question about this density. So for example, we already know stuff like, well, this density should be, well, either 0 or it's between 1 and r. And if I have a binary relation, then there's some probabilistic argument that says, well, you can realize any alpha between 1 and 2, and the density can be that. But there's an open question, I guess. I'm not sure who it's due to, but well, if I restrict my relation to be definable in NIP or a stable structure, can we get anything, or does it have to be a rational number or something like that? So it's analogous to similar questions about the VC density. So in ongoing work, what we can show is that if we have a semilinear relation, then this upper density should always be an integer. And then also using the same, or building on this thing, what we can show is that the VC density of any semilinear family should be an integer. Okay, I think I will stop here. So it's basically left on my side. So good, thank you.
All right, thank you. Let's thank Abdul Basit. All right, are there questions from the audience, online or in person? I guess I'll ask about, so I guess it was already known this connection between between these semi-algebraic graphs and this rectangle point incidence question, right?
Yes.
And so I guess so now you've created this subclass of semi-linear ones. And but had semi-algebraic graphs, like, had they only been considered over like the reals themselves, because now the semi-linear class, you don't need to work over R itself.
So I think there are results like this result by Galvin, Artem, and Sergey that I mentioned that generalizes the semi-algebraic thing to relations that are definable in digital structures.
Oh, okay. I see.
So I think I mentioned it somewhere. Let's see if I can find it. Go ways back. Yeah, this particular result, I guess, is that.
I see. Yeah. And then one more question. So you mentioned at one point that you can improve the bounds when you just consider rectangles where the endpoints are dyadic rationals. And so I didn't quite see, how does that factor into the proof, like the improvement? What's the mechanism?
So that I'm not completely sure about. So yeah, I couldn't answer that one. I'm sorry. They end up using that construction somehow to argue that the dimension must be big. And that in turn implies that there's upper bound on something.
I see. That's interesting. Yeah, I have a question. Yeah.
So is the lower bound construction you have for that dyadic case, is that the best you have, or?
Yes, so that's basically the best that we can say. And that's just the dyadic one. So if for other rectangles, we can't really say anything.
I see.
Also, in higher dimensions, it would be nice to say, for example, in 3 dimensions, you can get something that has a bigger power of log, because that would say things have to grow, but we can't even do that.
Right, so in the dyadic case, it's actually like sub-logarithmic, that extra term, but you think in general, it'll be just like a log n or something.
Yeah, I mean, I would expect, yeah, I don't really care too much about the log, I guess.
Yeah.
Even if we can get the power better, but yeah.
I see, yeah.
It should be a log or not.
Right, yeah, well, very cool, thanks.
Yeah, if there are no more questions, let's thank our speaker again. Thank you, Abdul. All right, we'll resume in like 2-3 minutes. Is that okay? Yeah.